Okay, so the big picture first. I see it, our exam, I strongly suggest, I mean, you can probably talk me out of this, but I strongly suggest that we wrap up Chapter 11 today, right? So we'll talk about this stuff, see how far we can get, maybe even get started on this, okay? Then Monday rolls around, and we answer questions on everything, right? So what's due for Monday, I see what's due for Monday. Well, we're not going to turn it in because I'd have to get it back to you, right? So, but if it helps you, what's due for Monday is all these problems and the review. That's really what's due for Monday. But honestly, I'm not going to collect it because you're going to need it to study for the exam. And then but if you have it all done, then we can answer questions on it, review, and exam. What time is lab? 3, 2, 2:30? Oh, yeah, unless you're Juan. When does he come in? How do we... He comes in later. Yeah. Okay, well, so he'll be an hour later. But that's the idea. So I think if you come in on Monday and if you haven't even started this, I don't think you'll have it done to study for the exam either. I mean, it just seems that way. But maybe, I don't know. It's all studying. I mean, it's all one thing. It's nothing. None of this is new. It's good review. Okay? It's all studying for the exam. Okay. So we'll try to get as far as we can today, and exact same thing Monday morning, and then our first exam Monday afternoon. So that means, again, the Spartan lab isn't due till whenever we do lab. We're not done with Spartan yet, are we?
No.
Okay, that's good. That's good. Okay, so I sent you an article and the article questionnaire, or you just pick up the questionnaire so you don't have to print it out. So that's also due, well, that's the only thing due Monday. That I'm going to collect. So here's a double slit experiment. Let's see what the movie's talking about here.
Now we are looking at the detector playing on the monitor.
Well, let me lower this a little bit. Rewind it. You gotta turn off the lights so you can see the full effect.
Now we are looking at the detector playing on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such conditions, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
All right. So
now we are looking at the detector playing on the monitor.
All right. So particles acting as waves, right? Passing through a double slit. Okay. Alrighty then. So we can start on these, or probably we should, right? I think rather than going back and seeing if there's questions on this, because that's kind of for review. So let's start on these. Yeah, it's true. Huh? Okay. The speed of a certain proton. We need some light. this question is kind of confusing. So we should definitely do this one together. Okay. What uncertainty in its location must be tolerated? Okay, well that means we're probably referring to which relation or what equation are we going to be using probably? It's not in the, I didn't get it to you this time in the back of chapter 11? No. Oh yeah, you're getting everything. Yeah, you're getting an equation sheet. I'll see if I can email it out to you. Right? But essentially, all I'm doing is copying and pasting all the relations that we've talked about. Okay, so let's find a relation here. We want to know uncertainty in a location. And the speed is that. Uncertainty in momentum is reduced to 0.01%. What do you think? You don't have much choice here. But they're talking about uncertainty in location. You only have one equation or one relation that refers to uncertainty in location or uncertainty in momentum. Heisenberg. What is that, page 5? Page 6? Oh. Okay. Yeah, that's it. Okay. So all we're interested in solving for is uncertainty in location, which is what symbol up there? What is it? Delta Q. Because P is position. Why do they have a Q in there? Why do they have a Q? Because position could be in X, Y, or Z. So it could be X, Y, or Z, right? Delta X, delta Y, or delta Z. Depends on the number of dimensions and things. So that's why they just have a Q in there, just to represent all three of them. And remember, momentum is a scalar or a vector? Momentum. What's the equation for momentum? mv, right? V is a vector, so that means momentum must be a vector. So, and they kind of leave this out, but if you wanted to talk about the x direction, you'd probably have a little delta px, right? The momentum in the x direction, and that'd be delta x, but okay, whatever, they don't really care. So what do we need to do here? This is where it's confusing. This is where it took me, what the heck does this have to do with anything? The momentum is reduced to 0.01%. How would you get 0.01% in here for momentum? What you need to do is, it needs to be this, right? Divide it by the momentum, and then you get 0.01, right? Or no, it's percent, so it would be, sorry, it was 0.01, now it's got to be 0.0001, right? Move it over two places to get rid of that percent. So pretty much that's what we have to do. We have to divide both sides by p here. And then this guy, that will just replace with the 0.0001. Now, what did we say? What did we say P was? Momentum. And what was the equation for it? mv. Do we know what v is? We know what v is. Do you know what m is? Mass of the proton. How do you get that? In the book. Right. Or just Google it. Yep. So we can solve for it. So our delta Q, we know everything, is going to be greater than or equal to h bar all over 2 times mv. Right? Oh, I forgot about my .001. Right. So we can find the uncertainty in our location if the momentum is reduced to 0.01%. Okay. Just have to know what it is. You have to know how fast it's going. Just put those numbers in. Does that make sense? Oh, yeah. Did we ever mention that? H bar is what? It's Planck, yes, but divided by 2 pi. And there's probably, it's probably in the inside front cover or something. But just divide, if you can't find it, just divide Planck by 2 pi. Ready to go on to the next one? Ready to go on to the next one? Okay. Let's see how yours is written. I changed the question. Hopefully I updated it, did I? So we're doing problem 5. Oh, it's the same. Change 2. Okay. Do the first one. The ground state wave function for particles confined to a one-dimensional box of length L. Now it's one dimension. Does that make sense in the equation? Is the wave function set up to be one dimension? Right? What's the one dimension? It's x, right? So are we using spherical polar coordinates? No. Our d tau in this case would be what? Just dx, right? Because there is no y or z, so you kind of leave that out, right? Okay. So suppose the box is 10 nanometers long. You use the wave function given and write a general expression to determine the probability of finding a particle between x equals a and x equals b. Okay. What's the general relation that you're supposed to be following here? All right. Let's see if I can find it. All right. To find the probability of where something is, we had to use somebody's blank interpretation of the wave function. That's where this is coming from. Right. Remember, let me set this up for you. This is kind of like let's use the Born. Let's use his notation, because I think the notation really guides you. You just got to get used to it, and then it really kind of tells you what. And plus, it's the only thing I give you on the quiz on the equation sheet, so we better know how to use it. Right? It looks like this. Right? And then what does that equal? That equals psi star psi d tau, right? Now, depending on what these limits are, you get the probability of where that box is. So if I went from, you get the probability of the box that it's in this boundary. If you see the boundary is negative infinity to positive infinity, all space, the probability is going to be 100%, which, remember, we don't use percents, though, so we're just going to say 1, right? If the wave function is the N word, not neutered, kind of, in a sense, you're right, if it's normalized, right? Is our wave function normalized? Is our wave function normalized? They didn't say it is, but look at this guy right out front. That would have been a good, this would have been a good homework question. Normalize it first, right? Don't give you this part and tell you to normalize this wave function, right? You'd set up 1 equals the integral psi star psi, right? And you'd make this an n out front. Remember doing that? We'll do some more, but they normalized it. They normalized it. Okay, and they probably should have said they did.
So 2 divided by L2.
Okay, so if we want to know, we want to set our limits to what? Not negative infinity and positive infinity, but A and B. That's it. And it's not going to equal 1 anymore. We'll find out what it equals. Okay. Integral from A to B. Psi star psi. Are there any little complex, any little imaginary numbers to worry about? No. So we just write the wave function twice, right? Now I could write d tau, but we know it's just going to be dx. Okay. Man, it would be nice to have that equation sheet, because then we'd have all those little integrals right there in that one sheet, right?
So my question is, did you not make them ahead of time, or did they just not write?
There's some stuff I just forgot to put in there. Like the articles and equation sheets. Okay. In fact, but I may not even have them because I don't have it either. So. All right. What should we do with the 2 over L? Take it out. Hopefully someone's going to remember this relationship. The integral from A to B of sine squared n pi x over L dx. It was like 1 minus cosine or some bloody thing.
1/2.
What is it?
It's 1/2 of 1
Oh, we better write it up here so we can substitute it in. It's 1/2, what, the sine square of what? Of ax? Of what? Sine square a theta. And it's the integral from what to what? Oh, it's just, it's a trig relation. Okay, trig relation. Sine square of a theta is the same as 1/2 1 minus cosine 2a theta. Okay, this is what we need. Thank you very much, Amberly. Yes?
Well, you're putting n pi x over here. Where are you getting the n from?
Oh, there's no n in there. Where am I getting n from? Yeah, thank you, Alice. There's no n. Just pi x over L. Okay. So 2 over L. So we don't get rid of that integral. That's not fun. So, we can pull out the 1/2. Right? Stick it out there. And we'll have 1 minus the cosine. Okay, of what? What's my little a going to be? Well, what's my theta? My theta is x, okay?
So
Pi over L, yep. So it'll be the cosine of 2 pi x over L. Now, we should be able to do this integral. I guess I could change colors here. Now it's just 1 over L. My 2's cancel. And we could break it up, right, in a couple integrals. The integral a to b of what? Yeah, that is dx, right? 1 times dx minus the integral a to b of that cosine dude. I mean, you don't have to do this, but I think it looks easier if you do it. Why am I still purple? Okay, the integral from a to b of dx. X evaluated from a to b minus, okay, the derivative of what gives me the cosine of 2 pi x over L? L over 2 pi. Let's try it. Evaluated from a to b. Take the derivative of that guy. L over 2 pi sine 2 pi x over L. Do you get cosine? We're close. You're just missing. Aren't we missing something? 'Cause isn't the derivative of sine negative cosine? Right? Isn't the derivative of sine negative cosine? Or is it the other way around? I don't remember. d dx of the cosine is the negative sign. That's it. So we're okay. Right? Right? Thank you, Madison. We're okay. Equals. Yeah, life is confusing enough. 1 over L. This would just be what? First part. B minus A. Thank you, Alice. Now we have minus. Okay. Can't really simplify it, right? So what are you going to write? I think you're going to have to write it all. I think you're exactly right. L over 2 pi. I guess you'd use parentheses. You didn't even have to write L over 2 pi twice. It's up to you, right? But sine of 2 pi b over L. All right. And then we have minus and minus. Since I don't have parentheses, I have to put a plus in here because I have minus and minus. All right. If you're using parentheses, you can keep your minus sign. And I didn't use parentheses, so I have to write L over 2 pi again. So So if you multiply through by your L, I guess you get L's to cancel. But essentially, you can't simplify it much more than that. You're kind of stuck. So you could find the probability just, all right? You could use this relationship to answer, right? If I said, I guess you could, yeah. You could put this in your fancy calculator, right? And if I give you this as the wave function, you could just plug in what those numbers are and actually get that probability all the time. Plug in what the limits are, plug in what the box length is, right? You have to show your work, so it wouldn't really count, but because that equals the probability. Yeah, this is, I guess we should write it in words. That's the probability of finding the particle between A and B. It has to be the magnitude squared. That's the Born interpretation. Psi star psi. Okay. Oh, now we just plug some stuff in, right? For B. Plug in 0 nanometers for A and 10 nanometers for B, and L is 10 nanometers, and get a number. But you can do that later, right? Should we just keep going? Those are just plug and chugs. Same with C. Oh, there's our nice little relationship right here.
Next time.
See? I forgot I was a nice guy. Okay. Oh, look at that. Do you see B? I mean, I was ready to start doing all this plugging and chugging.
When L equals
So what really, you better get what for B?
1.
You better get 1. Because it's the whole box. So I guess B is kind of a check. You did everything right if you get 1, because you know the answer has got to be 1. Because it's the whole box. So, I mean, you should plug everything in to see if it works, but you should really get 1 for that. Yeah, those signs are going to go away because the B and the L cancel, and you have sine of 2 pi. It's 0. Okay. Well, that's it. Now we're doing our review. That was a nice short homework, right? I thought we had a bunch. Okay. Yeah. Answer essay questions 1150 through 1153 on the back of this paper. What are they? Essay questions. Am I the only one who has a book? Probably, right? Where are the essay questions?
Yeah, I give up. You made this up.
That might be a carryover. I changed books at one point, but I don't... Answer essay questions 1150 to 1153. Well, I guess we don't have to worry about that.
All right.
Strange. Theoretical problems. All right, well, don't worry about that part then. I wonder if all this is messed up. 1150. How about 11.26? Does that make sense? Oh, this review is all messed up. Yeah, what a review.
So let's just tear this page out.
Well, I can just change it.
Yeah.
Okay, I gotta modify our review a little bit.
Found the chapter 12
All right, and problems. So you guys can get started on number 2 while I modify the rest of this stuff.
Yeah, it's not.
No, is the function obtained in problem 11.5 an eigenfunction of p hat x 11.6? Why or why not?
That was the one I just did with the fancy the long thing that should equal 1. And it does. Were you in a coma?
Okay, so how would you handle, since we don't have any essay questions to worry about, DWA, is the function obtained in problems 11.5, 11.6 an eigenfunction of p at x? Why or why not? Okay, how do you handle that? What is p? Find out what p hat operator is first. What is it? All right. There were several operators. We had Hamiltonian, right? I think we had position, and we had, these are the only 3 we talked about. We're interested in a momentum, p hat, and that was h bar over I ddx. Okay. Yeah, but it's so easy. Look at it. You take the derivative of that, or you can get the same function back again. Because look at what's your, I'm talking about the problem in 11.5. Take a look at him. Yeah, he's the wave function you just did.
So we use the function
What's the general relation you're supposed to be following for this whole eigenfunction business?
Operator function.
Okay, now the general operator, they used what? You're going to see what? That omega thing.
Omega hat.
F.
Is equal to, I call it whiskey, but that's not what it is.
Yeah, whiskey. Omega. No, what is that? I lost for a while. And then the next one is F. All right. So F is the
Because it's a W.
eigenfunction, and Rob's little whiskey thing is the eigenvalue. Okay. So it's an eigenfunction if an operator operates an eigenfunction, and you get an eigenvalue, a number, and the function back again. Okay. Do you do that? Do you get that for 11.5, the wave function in it? No, because it's a sine function, right? You take the derivative, you get cosine. There's no way you're going to get that function back again. Okay.
11.6 has an E in it, so.
Yeah.
That's-
All the E's, yes.
It also has an R, but it doesn't.
That's what it just says candy beans.
What is p hat in terms of spherical polar coordinates? I don't have it on handy. So we may not be able to do 11.6 because I don't know what. Yeah, let's just do 11.5. Okay. Well, I don't know what the momentum operator is in terms of spherical polar coordinates. I'd have to Google it and find it. That or it might be in a different chapter. But go ahead and start on number 3, and I'll see if I can find it in spherical polar coordinates. It's got to be in here somewhere.